Go ahead.
So, hi again. My name is Nik Erzetič. I'm a DevRel at Flare, and today's workshop will be about connecting EVM chains and proving payment in arbitrary token on another chain. So, basically, today's workshop will focus on another of the Flare data connectors attestation types, namely the EVM transaction attestation type. This attestation type allows us to get the data of another transaction from to get the data of a transaction on another EVM chain onto one of the Flare chains. And currently the supported chains are Ethereum, Flare, and Songbird. Now, I know that after the yesterday's lecture or workshop, this might seem a bit less powerful than the Web2 or JSON API attestation type. The thing is that the JSON API attestation type is only the latest one that we've added, and it isn't even fully added yet. For example, you cannot yet use that attestation type on the Flare main chains. Also, I'm imagining that in the future, the pricing for the fee for using each attestation type is prone to be much lower for the EVM transaction attestation type. So I think that there is use in this attestation type as well. Other than that, it is more convenient to use than the very cumbersome interface of the JSON API attestation type. So once again, we will be following the Flare Hardhat starter for this workshop. So let me Google that. This is the Flare Hardhat starter repository. If you are working from it, I recommend you clone it and follow the instructions in the README. There's also a version for Foundry available. So this one. And lastly, if you are interested in written guides about the attestation types, you can go to the Flare developer hub, and then click on FDC. And this is where you can find guides for both Hardhat and Foundry. So, before we get started, as I've said, I've already cloned the repository and went through all the steps described in the README file. I just want to mention something corresponding to the last workshop. So the yesterday's workshop. I of course found the bug immediately after leaving the stream, which is the reason why the thing I was looking for wasn't visible was because the function here was private. So if we turn it to public and run yarn hardhat compile, we can now find the data transport object, its ABI signature among the parameters of the ABI signature hack function. Okay, so with that out of the way, let's now focus on the main focus of today's workshop, which is the EVM transaction. So first of all, we'll be deploying an example contract called Transfer Event Listener. What this contract does, it filters through the events of a transaction data that we send to it, and finds out or actually stores the transfer events from the USDC contract on Sepolia in this case. So if we break down the code now, first of all, it receives the EVM transaction.proof struct, which is a struct in Solidity that holds both the data that we requested from FDC and the proofs which enable us to validate this data on chain. So this, what the contract does first is it validates the proof. Once again, it does this in the same manner as the JSON API attestation type by contacting the FDC verification contract, which does all the verification stuff for us. And then it, first of all, collects the event out of the response body, and it iterates through all the events. First of all, it discards all of the events that did not originate with the USDC contract. And then it also discards all of the events that aren't transfers from one address to another with the value. And if all of these criteria pass, it extracts the data needed and creates a new struct and saves it to an array that's public called token transfers. And the data of the transaction is stored as the token transfer struct, which basically has the fields of the sender, receiver, and the value that was transferred. Now, as for the, it has another utility function which just iterates through the whole of the registered events and returns them. But now, as for the whole verification process, yesterday I only breezed through it through the explanation of how this is achieved. But today, perhaps we have enough time to look at the contract registry. So the contract registry is a library Solidity that allows us to get official deployed Flare contracts through inbuilt methods or functions, instead of the more cumbersome and error-prone way that would otherwise be necessary. Basically, how the whole thing works is there is a contract, the address registry contract deployed on Flare, which has a method get contract address by name. It is basically a registry of all the official Flare contracts, and it is indexed by the contract names. It is done in this manner so that if one of the contracts gets updated, we can simply update its address, which means that the address updater contract always maintains the most current version of each deployed contract. And as I've said, we query the contract addresses by inputting their name. And this could be very error prone since we could make a typo, but we would also need to remember what the names of all the contracts are. So instead, what we do is we provide a Solidity library that inlines these function calls into our code for us. And for example, if we try to access the what's it called, the FDC verification contract, like we do within the EVM transaction or within the token transfer event listener contract, we can just call the get FDC verification function within the library, and it will inline the code, which is this. It is get contract address by hash, or rather it is the IFDC verification contract at the address that we get by calling the address updater contract with these parameters here. And as you can see, it's much more cumbersome to do it this way than the way we do it within the example contract here. So before I continue, I'll once again explain the steps that are involved within the whole process of getting data through the FDC onto the Flare chain. And for that, let's once again look at the diagram for the user workflow on the Flare Developer Hub. So let's just open the image in the new tab and let's look at it. But let me take a sip of water first. So these are the steps involved in getting data onto one of the Flare chains. Well, first of all, there is some data that we want to get access to. In this case, it is a transaction on another EVM chain. We need to formulate an ABI encoded request that the FDC protocol is capable of understanding. And we could do it manually, but the more convenient way is to send our request data to a verifier server, which will prepare the ABI encoded request for us. And then we pass the ABI encoded request to the FDC protocol. And in the background, the data providers will get the data for us. They will submit the proofs for that data to the FDC, and that will be written on chain. And once the current voting round has finalized, we can request the data from the data providers, and they will also give us their proof, and then we can go back on chain through our smart contract and verify the proof there. So basically, the only thing actually stored on chain is the proof for the data. That is the Merkle root of the Merkle tree that is constructed. And otherwise, the data is stored off-chain with the data providers, which makes the whole thing a lot less expensive as far as the gas price is concerned. So with that, we can now look at the script that runs the whole procedure. It is aptly named the EVM transaction .type script. Here at the top, we can see the request data that we'll be sending, and it's just the transaction hash of the transaction we are looking at. So let's first of all look at this transaction on the Sepolia Explorer. So let me write Sepolia Explorer, and it's this one. So without the quotation marks, cool. Huh. That's quite interesting. Perhaps without the, oh yeah. There it is. So this is the transaction that we'll be accessing. If we look at its logs, we can see that there are a few different events: a deposit, 2 transfer, actually 3 transfer events, 1 swap event, and another transfer event. These 4 transfer events are the data that we will be collecting in this example. Let us also look at the USDC contract. Perfect. So we could just pick a random transaction from here. No, let's keep the one in the example. Anyways, so let's go through the code for this contract real quick, or rather, let's first look at the configuration data. As I've explained, the transaction hash is the hash of the transaction that we're trying to get. But unlike with the JSON API attestation type, now the configuration constants matter. So test ETH signals to the FDC protocol that we are trying to access a transaction that happened on the Ethereum testnet, so on Sepolia. Equally, the ETH in the URL type base helps us to contact the correct verifier server for that. If we wanted to instead get a transaction on Flare, we would replace ETH with FLR, or for transaction on Songbird, ETH, we would replace ETH with SGB. Another thing to note is the small letter test preceding the ETH symbol. What this means is that we are trying to access a transaction on a test chain and not on the main net. The current configuration only allows us to access mainnet from the Flare mainnets and test nets from the Flare test nets. So, for example, since we are deploying our contract on Coston 2, which is the Flare test net, we can only access the other test net chains, which are Songbird, Coston, and Coston 2. But if we deployed our code to Flare, then we could access the Ethereum mainnet as well as the Flare and Songbird chains. Let's now look at the main function. It's very similar to the one with the JSON API attestation type. So we first prepare the data, send it to the verifier server, which prepares an ABI encoded request for us. Then we submit the ABI encoded request to the FDC, which then it commits it to the Pro protocol. The whole machinery runs in the background, and we have to wait for the for all it to happen, and then we can retrieve the data in proof of our transaction. Then we just deploy our transfer event listener contract to, in this case, custom 2. We can interact with the contract with just deployed contract by sending it the transaction data as well as the proof. Now let's look at the contracts in more detail. So first of all, prepare attestation request. What it does is, first of all, build the request body for this attestation type. And how does it know what the request body is supposed to look like? Well, we can see that if we go to the example environment and follow the link to the URL testnet, which of course is blank so far because we need to add verifier and then API doc. And this opens up an interactive documentation. Now, if we scroll down to prepare attestation request and be mindful of the ETH, although it doesn't really matter in this case because of them are virtually the same, just the address is different. So anyways, if we open that up and click try it out, we can see what the prepare request body or the whole prepare request is supposed to look like. And specifically, what the request body is supposed to look like. And we can also see down there, or let me actually zoom this. We can also see what the return will be, which is just the status and ABI encoded request that we need. So with that in mind, we can look at the code again. So request body, we're providing to it the transaction hash. There are some additional values that we have hard-coded. So required confirmations, this is the number of blocks that we need to look, that need to pass before we consider a transaction passed or as confirmed. There are additional values that you can find if you go to the official specification. Let me just show that real quick. So if we go to FDC attestation types and Flare Developer Hub, we can go to EVM transaction. There's the specification if you really need to change these values, but that's not strictly necessary, and that's why we're just including them as a default. So once the request body has been prepared, we also need to prepare the URL, which is constructed from the URL base, and that is the one from the environment, the one that opened up just a second ago, with the appropriate source base, so URL base, and that swaps values that are included into the URLs, so we are accessing the correct endpoint. We also need the verifier AI key, which is set up within the .env file. But yeah, With that, we can go to the prepared attestation request phase, which additional values to the request. And if we look at this again, so attestation type and source ID, well, these are just UTF-8 hex string, hex encoded strings padded 32 bytes of the two values that that I kind of glossed over at the beginning. So attestation type base gets hex encoded to that value, and source ID base test ETH gets encoded to the second one. And I think these two values here are the correct values. Anyways, so with that, the whole request can be prepared and posted to the verifier server, gets us back the ABI encode request. And with that, you can submit it to the protocol. And this one is basically the same for all attestation types, and so we can just use the base function that is shipped with the starter kit or the starter pack. So the substep, let's the diagram for that is this one. So number 3 as is labeled here. For that, we first need to access the FDC hub contract somehow. This is a official Flare contract. We also need to calculate the request fee advanced. The fee is theoretically dependent on the attestation we are making. So we provide the correct contract with our ABI encoded request. So far, the fees are constant and the same for all attestation types, but as I've said, they're prone to change in the future. Let's just get a quick look at the request fee. So basically, we are contacting another of the Flare's deployed contracts or official contracts, which FDC request configurations, and we call it get request fee the method at the request fee. And let me find the function. So with that, we can call the requestation function on the FDC hub contract, and we do also pay the appropriate request fee. So after, the only thing remaining is to calculate the ID. Let's get that in more detail as well. So what we do is we get the block number of the block containing the transaction in which we requested the attestation to the FDC. Then we get the block timestamp of that block, and with that, we first of all contact another official Flare contract, which is Flare Systems Manager. This one will give the times of the first voting round, or the start of the first voting round, and what the duration of a voting block is in seconds. And with that, we can then calculate the round ID of our transaction, of the transaction in which we submitted the attestation request, and do this by subtracting the first voting round start timestamp from timestamp of walk and divided it by the voting epoch duration in seconds. And of course, because these are integers, it will round to the correct integer. So that is the submit step. Now, what needs to happen is we need to wait, but that is already encapsulated in the request proof and data, retrieve proof and data function. So the retrieve proof and data function contacts the DA layer provider at a certain URL, or rather, it first contacts another official Flare contract, which is the relay contract, and that is the contract that's able to tell us whether our round has been finalized. And the number 200 here stands for the FDC protocol, whereas the number 100 would mean that we are trying to access the data about the FTSO protocol. So anyways, the relay contract can tell us whether the round has been finalized or not. If it hasn't been, we wait for 30 seconds. We wait 30 seconds for it to finalize, and then once it has finalized, we send a request to the DA layer provider to get the data improved. And since the DA layer provider needs some data to crunch the numbers and calculate the proof, it may not update instantly, and so in that case we repeatedly wait additional 10 seconds until the round has finalized, or rather until the layer provider server has updated. And so with that, we can then deploy our contract, which is very straightforward. And we can, after that, interact with our contract. And what we do is send in the proof that we got back from the DA layer provider, which we first of all need to decode, because let's look at the response that we actually get back. So custom to data availability, and once again, let's append to that API doc. The endpoint we are accessing is the proof by request round raw, which accepts the voting round ID and the request bytes, and it returns an array of proofs, an attestation type value, which should match the hex encoding of EVM transaction string, and then the response hex, which is ABI encoding of a certain solidity struct, which is defined. If we look at under the node modules, Flare network, Flare periphery contracts, custom to, and then IEVM transaction solve, the struct we're getting back is the IEVM transaction dot response. This is so we're getting the encoding of that, which means that if we want to access the data, we need to decode that string to an appropriate struct, and we do this through a hack. I mean, we could just copy the ABI signature of that struct here, but instead we are getting it from the hard hat artifacts through this ugly thing here. Anyways, with that, we can decode the response hex to a EVM transaction dot response struct, which is in this case just a JavaScript object, and then we construct an EVM transaction dot proof struct, which just has these two fields, which are Merkle proof, which is the array of proofs that we got back from the layer provider, the layer server, sorry, and the data, which is the decoded response. And we send this to our event listener contract, which then does everything that we've seen at the start of the workshop. So with that, let's now run the whole script. And let's be fancy this time and do terminal run selected text in active terminal. Let me get a sip of water. So what's happening here is, first of all, we prepared the request for the verifier server. This is what we sent to the verifier server. We got back a valid response and an ABI encoded request. And then we see that the round that we calculate is this one here. And we can also just follow the link displayed here to see the progress of the round. Okay, so first of all, what this tells us is that all of Flare's data providers claim that they can retrieve the data and construct the proof. So I think that let's try to find our transaction. It would be this one, the last one. It has 80% support, which is enough. And if we look at finalizations, I don't believe, no, the round hasn't finalized yet. We're waiting for the round number 65 to finalize. We can also see a mismatch here, which is all right. That is because we create another contract to get round number, and because of latency, it's a bit different. But that's just a thing for to make sure everything's working fine. Anyways, the round has finalized. We got back, or rather, we prepared a proof request that we now sent to the DA layer server. And what we get back is this proof here with a very long response hex, and as we can see, the attestation type here matches the UTF-8 hex encoding of the string EVM transaction, and these are the proofs. In this case, there are multiple values. The proof could also be the empty array, in the case that our request was the only request that's round, because in that case, the Merkle root would be the proof for our data. We can also see that our contract has been deployed and verified at this address here on the Flare Explorer. The little green arrow here represents or means that the contract has been verified. We can also look at its code down here and its functions. We can also call the functions here. So for example, we could get token transfers, and we see that there are 3 token transfers with between certain addresses and with this value here. We can also see the transactions that happened, so the contract creation and the collect transfer events call. and this one is the one, let's see, the one fitting the transaction hash here, and this is the output of the get token transfers function. We can also see a decoded proof right here. And so one last thing I'd like to show you is how we would add the data of another transaction. So let's first of all get the contract address and go to the EVM transaction script. What we need to do is comment out the creation of the event listener, and instead do, let's just let the AI do it. So let's await EVM transaction at the address, and let's paste in the address of the contract that we have just deployed, and let's also find a suitable transaction. Let's just grab the first one and see what happens. So that is the transaction on the Sepolia Explorer, and let's just run the code again. And so this is more or less it for this workshop. Now it's time to ask the questions. If you have any, do that in the chat, please, while we wait for the whole mechanism to run. Oh, another thing I should probably mention is that if you need API keys, if you need keys for API keys for either the DA layer server or for the verifier server, you should ask in the Flare Discord or in the Flare Hackathon Telegram group. And someone there will be able to provide those for you. Okay, so while we are still waiting for the questions, let me also mention that give us a little preview of the lecture on Monday. So in that workshop, we'll look at the proof of reserves example within the Flare Hardhat starter, which basically combines the two attestation type that we've looked at yesterday and in today's workshop. It is a way to verify, or it is a functioning dApp, which you'll see what it does on Monday, I guess. Or no, actually, this is a good example of a script that will never come to an end, because our request was basically declined by the data providers. So I guess the transaction isn't suitable.